Okay, thank you. I start 20 minutes. So thank you for inviting me to this forum. First of all, I would like to thank the people that work with me in this project. And most of part of this presentation is in the framework of the PhD thesis of Mihalis Corres in work with the EDF in France. So the idea, yeah. So the idea is this is a picture that you know very, very well, but the idea is only to place or work in this, in the earthquake loss estimation flowchart. So for instance, in this part of the work, we have to define the natural hazard, the site effects, and study the risk assessment in order to estimate the risk. And in the convolution of all these points, you have the expected loss. The presentation of today is a mix between these first two parts, is to take into account the natural hazard and also the site effect in the soil interaction structural response. The approach that we use here in Central Supelec and in our team is named an holistic approach. The idea is to try to understand the mechanism that control the induced damage in earthquake loss estimation, it be in the soil foundation, structures, or dams, and so on. Also, we try to improve and validate the traditional approach and evaluation methods that are usually applied in the engineering practice. In most of the case, we try to take into account the nonlinear soil behavior. It's not for today, but we are able to perform this kind of things. And the most important part for us is that we use principally numerical methods in order to facilitate the comprehension of global problem via always a parametrical analysis. So it means that we need huge computational capacity in order to perform this kind of analysis. And why we use this? The idea is to estimate the seismic safety, principally for strategic facilities as dams or nuclear power plants or bridge or another. And we try always to introduce certain uncertainties in the material properties, loading parameters, and scenarios. So this is the case today, and it's not for the presentation of today, but the idea is to, due to the fact that the computer model can be computationally expensive, we try to introduce the surrogate model or the meta model, like as Roberto showed before. So for today, I try to point 3 points to develop. First of all, to talk about the model that we use to perform physics-based 3D ground motion simulation. Show you one case, one study in the PhD thesis of Mihalis Corres related to the aftershock of Niigata-Ketshu earthquake in 2007. And then we move to the soil interaction structure coupling. So for the first part, the idea is, the first question is the thing that we want to simulate. So we want to simulate a 3D regional scale model. It means go to 10 to 100 kilometers, at least with the engineering frequencies. It means 10 or 15 hertz or a lot. But for instance, we are close to 10. And for that, we need computational power. So it is able to have a supercomputation, supercalculators. We have some time to perform the computation there. But the most important is that we need to a code that is able to work in massive parallel architectures. And also one key point is the details on seismological and geological scenarios. And it's not all times is the case. And the next step is we don't need to perform a large computation with nonlinear in this case, but we can coupling this with a nonlinear numerical code, as David showed in the introduction this morning. So in our team, we use the code SIM3D. Is similar as Roberto showed before. It's a spectral element code, and this is working in the framework of the French project Synapse, and we work together with the COA and IPGP. So this code allows us to perform a 3D simulation from source to site and even to a structure, and it's worked by blocks. So we have a block that generates the meshing, for example, and other blocks that take into account the geology, topography, bathymetry, for example, and other blocks that work with the seismic source, the nonlinear behavior. We are able to produce a random field, and we put together as a Lego approach, and we are able to perform the large computation. So now we move to the application case. So the first case is as I say, the aftershock of the Niigata earthquake. First of all, we start with this is in another thesis in this project. We started to make a coupling between the regional geologic structure that we found in the literature, for example, this one, Tatsuda et al., and we coupling this model with the mesh of the site. So here we have some characteristic of this mesh. We use actually two mesh for that is not the same dimension in the picture and in the text, but we are close to 4 million of elements and 1 billion of degree of freedom. For this case, we have a maximum frequency of 5 Hertz. So the first thing is to improve the geological model. As for that, we start from a 1D profile that we found in the literature several profiles for the site. As you can see in this picture, the distribution of shear wave velocity with depth and the different model proposed by the authors. And the most important thing is that we are able to couple in both this shear wave velocity and this geological structure. And the most important thing is the apparition of a folding, as you can see here in this picture. It's placed here in the yellow line, the map, and in the other place we don't take this fold, take into account this fold. And here we have one of the aftershock that we will talk. So, but if we go deeply in the geological aspect, we found also another work, recent work provided by the Sekiguchi et al. From the Geological Survey of Japan, and they provide a geological 3D model of the region. And here we can compare for two cuts at the right side, the geological model provided by the Geological Survey of Japan, and in the left side we have the approached model from the 1D and coupled with the folding here in this case. So this is for us, this was a question, what is the effect of what to take into account to one or other geological model in the response, in the global response of the site. So if for that we build three models. The first one is a model named Z, that is purely the 1D model coupled with the folding, is this one. And the other stream is the model R, is provided by the Geological Service. And we mix both in a model, taking the surface with the folding, and in the depth with the regional geology. Sorry. So now we move to the validation aspect, and it is important. So in this case, we simulate with a point source the aftershock of 1, it's a magnitude 4.4, and we take all the station Kashiwazaki Kariwa nuclear power plant. So here we have several records that we provided in the CARISMA benchmark. And here we can see, for example, a comparison of one of the records and one of the simulation or synthetic simulated with one of the model. And this is the gooseness of fit criteria proposed by Kristrekova. And here we have the statistic of several points. So we can see that here we have in the blue dot the regional model, and in the orange dot the simplified model. But we can agree with you that some points are very far from the good, provide us a good response, but we have some points that the response are very good, even in FAS and in envelope. So we have a high score of 9 or 8. So for instance, we can say that we consider that the model, the global model, both are validated. So in order to go far, we try to provide several scenarios. So we try to simulate several extended source, even if it's a magnitude 4.4. We use a typical model from the region of Japan. So we put here this source, and we use a kinematic source with a RIC model. And here we provide the depth of the strike rate and dip of this source, and we test several scenarios. This is allowed in the code of RIC. We can test several permutation of point and statistically agree with the sleep distribution that we provide at the beginning. And here we compare with a traditional GMP the response for the model, simplified model, the regional model, and the mixed model. The comparison for two spectral acceleration at a period of 1 second and 3 seconds, and as a function of the distance. So each point, and you see that we agree more or less with the mean and more or less one standard deviation of this GMP. So we consider that in this case, it seems that the fact that you use the simplified model or the regional one are not to provide some difference. So now we can move to the SSI coupling. In this case, so we, as I said before, but the other presenters, we use the RM coupling. It means that we will coupling the same model. So it's here the regional case. So here you have one of the simulation. And here you can see a little point here that is the final element model, that it is summarized here. So we have a reduced model that is simulated with a finite element code. In this case, the code Aster is a French finite element code. And here we have a picture of the one time of the nuclear power plant, and so we can see the deformation, etc., etc. So this coupling allows us to introduce the complexity of the incident wave, taking into account the regional geology and also the folding case, etc., etc. So for this case, the first one is to compare what is the impact of the regional geology. So we have I don't have a lot of time, so I will compare only the model R, that is the geological one, and the model, the mix of the simplest one geological case and the regional geology. It means that at the depth, we have the same properties that you can see here, but in surface, we can see that the model Z have the folding and the model R don't have the folding. So for that, we compare, we take into account 12 kinematic source, again, provided by the RIC model, and we compare if we take a point close to the fold. The idea is that we must have the same response. This is the case. So here we have the difference between the response of model R less the response of the mixed model one. And we can see in this plot, in terms of the frequency, make attention because the previous presentation showed this one in terms of period, but we show this in terms of frequency. So you need to change in your mind. So we can see that it is equal to 0. We have some spurious points here in the lower values of frequency. We don't know exactly why, but we try to explain this one. But we can see that in the most of the frequency range, we are close to 0. So it means that we introduce the same source in both models. Okay, now we can see, for example, what happens if we take into account the response at the top of the structure. So here in this point. So we have the same comparison. So if the response is positive, it means that the response is higher in the regional one, and if the response is negative in this axis, it means that we have an influence of the presence of folding. So here we can see that for the two horizontal components, the first two one, we can see that most of the response are close to 0 or positive. It means that for the lower values of frequency, close to 3, for example, we have the response is dominated by the global geology. However, when we move to higher to frequency of 3, we can see that the most of the response are negative. The ratio is negative. It means that we have an effect of the presence of the folding. So this is interesting because it means that if we use we don't make attention with the position of the source, that in this case is the north of the folding, and the presence of this folding, that even it is a 2,000 kilometer depth, it have a very high effect in the response of the structure. It means and it may be important for the nuclear power plant. So we can compare as you thinking, we can compare at any point in the model. But for us, the most important thing is to see what happened with the mean values. For example, for a point that is at close to the fault. Okay, so this is the red line. One point that is placed at the free field in the surface without the structure, and one point that is placed at the top of the structure. So we can see that for the two horizontal components, we have more or less the same response related to the amplification. It means that is dominated by the regional model for the lower values of frequency, but for the higher values, higher than 3, we can see a huge difference between the mean values obtained at the free field and at the top of the structure. We can see that for the top of the structure, the difference is less than the one for the free field case. It means that it seems that in this case, you have here the frequency of the main frequency of the building. We can see that we can say that the structure smooth or reduce the impact of the depth geology. So this is interesting, but we don't know if we don't have the structure. On the contrary, for the vertical case, we have an opposite behavior. It means that the presence of the structure increase the effect of the presence of folding. So I think that this is again an ongoing work, and it is interesting, but I think that this is a good point. So now have less than 1 minute. I move to the partial conclusion. So here some key points that the sensitivity analysis that we done show that the regional complexity and folding, which means the Setter model, have an impact after 2 or 3 hertz. It seems, however, it seems that for the vertical component, the response seems to be controlled principally to the regional complexity, and the presence of the building reduce the effect of folding, and the presence of building, you can know the other conclusion that I provide you before. So the next step is to evaluate the effect of different source position and to increase the range, the frequency range. So thank you for your attention. I think that I have in the time.
Very good, excellent.